In the next 4 minutes, we're going to prove the Tan-chord theorem in 4 easy steps. So what's the first step? The first step is to make a construction, right? So we're going to construct a diameter that passes through point O, obviously. So if I do that, we're gonna have something like what I just drew on the left hand side, and then we can name that point on top of the circle point Z, right? And then we can join D and Z. You don't have to name it point Z. You can name it any letter you want. You can name it Y, you can name it Q, and so on. So we have done step number 1, and then now we can move to step number 2. What is step number 2? Is to show that this angle here is equals to this angle. And then how do we show that? So we're gonna say angle DZF, F is here, is equals to angle E, because they are subtended by the same chord DF, right? So this chord DF is subtending this angle and this angle, so the angles must be equal. And with that said, we are done with step number 2, and we can move to step number 3. So step number 3, we're going to prove that this angle DFK here is also equal to angle DZF, right? And then if we can prove that, then we have proved that DFK is equals to E. So let's see how we will go about that. So we can see that angle ZDF, this angle here, is equals to 90. That is because it's subtended by a diameter, right? So we're gonna say angle ZDF equals to 90 degrees because it has been subtended by a diameter. A diameter always subtend an angle of 90 degrees, right? So now that we have said that, let's calculate the value of DZF, right? So if we use the sum of angles in a triangle, we're gonna get DZF plus angle ZDF plus angle DFZ equals to 180 degrees. So what is the size of DZF? Is the angle we are interested in, right? So we're gonna have DZF plus ZDF. ZDF, we just say that it's 90 degrees plus DFZ equals to 180 degrees. So if we take this expression to the right hand side, we're gonna get angle DZF is equals to 180 minus 90 minus DFZ. So DZF will just be equals to 90 degrees minus DFZ. So that's it. We have determined DZF, and is equals to 90 minus DFZ. Now we are just left with proving that angle DFK is also equals to 90 minus DFZ, and we are gonna be done. So if you look on our diagram, you will realize that this angle KFZ is 90 degrees, this entire angle. That is because where the radius and the tangent touches, they form 90, right? So we're gonna have DFK plus DFZ equals to 90 degrees, right? And then if we make DFK the subject of the formula, we're gonna get DFK equals to 90 minus DFZ, right? So now we can see that DFK is equals to ZF. But we know that dZF is equals to E, right? So that will all be equals to E. And by that, we have proved the Tan-chord theorem. So you might be asking yourself, is that all, or do we have to do something else? Yes, we have to do something else. Step 5 is to subscribe and like the video. When we do Euclidean geometry, we are guided by the keywords and nothing else. So for question 9, it's saying that in the diagram below, P, Q, R, and S are points on a circle. Clearly, and then PS, PQ, PR are produced to V, T, and W respectively. VT is parallel to SQ, right? And then we know that there's a lot we can deduce from lines being parallel. So that can count as a keyword. So VT is parallel to SQ. And then it goes on to say that SR is parallel to VW. So our second keyword, SR, is parallel to VW. So we must be able to answer all our questions using these two keywords, except from the basics. Things like angles on a straight line, angles on a triangle 18 to 180, angles subtended by the same chord. But these are only the keywords we're gonna need to answer this question. So 9.1 says, prove given reasons that TQ divided by QP is equals to WR divided by RP. So where's TQ? So we have TQ here divided by QP being equals to WR divided by RP. Okay, so let's look at the first keyword. The first keyword says VT is parallel to SQ, right? So let's look at the VT. VT is this line here, and it's said to be parallel to SQ. SQ is this line here. If those two lines are parallel, then the sides PT and PV will be divided proportionally, right? In triangle PTV, if QS is parallel to VT, then the two sides will be divided proportionally. What are we saying? We're saying that TQ divided by QP will be equals to VS divided by SP. We can only say that if we have two lines that are parallel on the triangle, right? They will divide the two sides proportionally. So that's all we have deduced for now. Let's move on and go to our second keyword. Our second keyword says that SR is parallel to VW, right? So let's erase these parallel lines for QS and VT, and let's pay our attention to SR and VW. So where's SR? SR is this line here, and then we have VW, which is this line here, right? So if those two lines are parallel, then in triangle PVW, right? PVW, the two sides will be divided proportionally. WR divided by RP will be equals to VS divided by SP. But then how does that help us answer our question? I want you to realize something here. We're saying that TQ divided by QP is equals to VS divided by SP, and WR divided by RP is equals to VS divided by SP. We know fully well that if A is equals to C and B is also equals to C, then A and B are equals to each other because they are all equals to C. So if we apply the same idea here, we're now saying that TQ divided by QP is equals to WR divided by RP. Why are we saying that? They are all equals to VS divided by as P, and we have proved what we are required to prove. Let's move to 9.2. 9.2 says, let's prove given reasons why TP-VW is a cyclic quadrilateral, right? So let's look at TP-VW. So we have T here, we have P here, and then we have V, and W is here. And then it is said that we must prove that it's a cyclic quadrilateral, right? So it's a cyclic quadrilateral if those four corners can lie on the circumference of a circle, right? So we must be able to draw a circle around TP-VW, and then the 4 points lying on the circle. So let's just construct a circle. It's not really clean, but yeah, this is what we essentially saying when we saying that TP-VW is a cyclic quadrilateral. We should be able to construct a circle around TP-VW, and all the points lie on the circumference. So I want you to realize something here. If these points lie on the circumference, then angle T should be equals to, don't forget we have W here. Angle T should be equals to angle W, because they are getting subtended by the same chord PV, right? That's if indeed it's a cyclic quadrilateral. So if we can prove that, angle T is equals to angle W, then we have proved that TP-VW is a cyclic quadrilateral. Because if indeed it's a cyclic quadrilateral, then T and V should be equals to each other, because they will be subtended by the same chord PV. So let's find a way to connect T and V using the circle we already have and our parallel lines. Let's go back to the keywords again, because we agreed that for this question, we're only gonna stick with the keywords, right? All questions on Euclidean geometry, you stick to the keywords and nothing else. So the first keyword says VT is parallel SQ. So VT with parallel SQ. If VT is parallel SQ, then Q1, this angle Q1 here, should be equals to angle T. Q1 and T are corresponding angles. So let's write that down for the sake of clarity. So we're saying Q1 is equals to T, because they are corresponding angles, right? And then let's go back to our keywords. So we've used the first one, we are only left with the second one, right? SR and VW. If SR, let me make SR clear. So if SR is parallel VW, then angle R1 should be equals to angle W, right? They are also corresponding angles. So let's write that down. So we're saying R1 is equals to W. But we need the T to be equals to W. So we have to find a way to relate Q1 and R1, right? If we can prove that Q1 and R1 are equals to each other, then T is equals to W. So how can Q1 be equal to R1? Let's look at our diagram. So we have Q1 here, and we're saying that it must be equals to R1, right? And then indeed it is, because PS subtends Q1 and it subtends R1, right? So now we can say that Q1 is equals to R1 because they are in the same segment, right? So T is equals to Q1, but Q1 is equals to R1 and R1 is equals to W. So T and W are equals to each other because they are all equals to Q1 and R1. So by saying that, we have essentially proved that TP-VW is a cyclic quadrilateral. This is the easiest question because all the answers are given to you on the statement, right? So let's look at this. In the diagram below, BOA is a diameter. We know that in Euclidean geometry, a diameter is important to us, right? So let's take that as a keyword and write it down. So we have diameter, right? And then it goes on to say that of the circle centered at O, BA is a tangent. So let's write that down, tangent, because we know that we have the Tan-chord theorem, and where the tangent and the radius meet, we have an angle of 90. Now let's go on and see what else we have. We are told that EA cuts the circle at D, right? And then F is the midpoint of AD. So let me show you what we're talking about. So EA cuts the circle at D, and then F here is the midpoint of AD. If F is the midpoint of AD, then this angle here should be 90 degrees, and this angle should also be 90 degrees because of theorem 1. So let's write that down. We also have theorem 1. And then that's all the information we have, right? We don't have anything else. So we should be able to get the 11 marks for this question only using these 3 statements. So let's see what happens. We have 9.1.1, which says that let's prove given reasons that OBEF is a cyclic quadrilateral. OBEF is a cyclic quadrilateral, right? So let me just highlight OBEF. So here's OB, and then we have EF, and this should be a cyclic quadrilateral. So back to the definitions, right? If it's a cyclic quadrilateral, then what should happen? O1, right? This angle O1 should be equals to this angle E. The exterior angle should be equals to the interior opposite, right? Or F1 should be equals to the entire of B. That's if indeed it's a cyclic quad. So that's what we're essentially trying to prove. And then how are we going to prove it? We are going to stick to these 3 keywords that we have. So let's look at the diameter, right? Because the first keyword is diameter. So we have our diameter OB. Our diameter subtends angle D, right? Which is 90 degrees. But then that's all it does. It has nothing to do with what we're trying to prove, right? So at this point, our diameter is failing us. Let's move to the tangent. So we have the tangent EB, right? Which is subtending A. So now we can say that angle B2 is equals to A, but then that doesn't help us with anything, right? So we cannot use the tangent to answer this one. Let's look at theorem 1, right? So by theorem 1, we have already said that this angle F1 here is 90 degrees, right? We know that F1 is supposed to be equals to the entire of this angle B here, right? So now let's just say that F1 is equals to 90 degrees. Why are we saying so? We have a line from the center to the midpoint of a chord, right? That angle there should be 90 degrees. But then we need the entire of angle B to be also equals to 90 degrees. And then we will have proved that OBEF is a cyclic quadrilateral. And indeed, we can say that our angle B is equals to 90 degrees. And then you might be asking why. Why are we saying that? That is because the tangent will always be perpendicular to the radius, right? So that angle there should be equals to 90 degrees. So since angle B is equals to angle F, we have our cyclic quad because an exterior angle will be equals to opposite interior angle, as you can see. And then now let's do 9.1.2. So for 9.1.2, we're supposed to prove given reasons that triangle ADB, it's similar to triangle BDE. And let me tell you something, right? So the way they name their triangles in an examination, right? Angle A here should be equal to this angle B on the other triangle, and then angle D should be equal to angle D on the other triangle, and then consequently B and E should be equal to each other. So what are we saying? We're saying that let me just highlight the triangle so that we can have a bit of clarity, right? So we want triangle ADB, right? So let me highlight that. So we have triangle ADB, and then there we go. And we're also looking for triangle BDE, right? So we have BDE, right? So we're saying that angle A should be equals to angle B. So let's look at angle A here. Here we have angle A, right? We're saying that it should be equals to this angle B here. So let's go to our keywords and see which keyword we can use. You can already see that we're going to use the tangent, right? Because EB is a tangent and BD subtends angle A, right? So already here we can say that angle A is equals to angle B. And then why are we saying that? This is because of the Tan-chord theorem, right? And then now we can go ahead and see that angle D in triangle ADB is equals to angle D in triangle BDE. So we're saying that this angle here should be equals to this angle here, right? Which keyword are we going to use? We have diameter, tangent, and theorem 1. We're going to use diameter in this question, right? Why are we saying diameter? Because D1 is equals to 90 degrees. Why are we saying is equals to 90 degrees? It's being subtended by a diameter, right? But then at the same time, D1 plus D2 should be equals to 180 degrees, right? This is the sum of angles on a straight line, right? The sum of angles on a straight line. So you can see here that consequently D2 will be equals to 180 minus 90, which is just 90 degrees. So now D1 is equals to D2. They're all equals to 90 degrees, right? It becomes easy to see now that this angle here B1 should be equals to the angle E, because they are the only remaining angles, right? So now we can see that B1 is equals to angle E, right? But then you don't have to say this, but then I'm just assuming that we might need to use it when we solve other problems. Let's move ahead with our equation. So we have 9.1.3. So 9.1.3 is saying, let's prove given reasons that OB is a tangent to the circle passing through BDE. So let's construct that circle so that we can have clarity, right? So we want a circle passing through BDE. So it's a circle that looks something like this. It's passing through B, it's passing through D, and then it shall pass through E. So it's a circle like that, right? And now we have to prove that OB is a tangent. If OB is indeed a tangent, then the Tan-chord theorem should hold. This angle here B1 between a chord and the tangent should be equal to this angle E here, right? Which is subtended by that chord. How can that be true? That's what we were talking about in 9.1.2, right? That the true angles of those true triangles are equal to each other. So the remaining two should also be equal, because all those angles add up to 180 degrees in a triangle, right? So now we're just going to say that B1 is equal to angle E. And then why are we saying B1 is equal to angle E? Because third angle in a triangle, right? The third angles in a triangle should be equal to each other if the other two are equal to each other. And then where is the privilege to say that coming from? It's coming from the fact that triangle ADB is clearly similar to triangle BDE, right? Like we just proved. And now we can do 9.2, right? So 9.2 says that let's prove that OF squared is equals to AD, not triangle D, but AD multiplied by DE divided by 4. So as soon as you see a question asking you to prove something like this, right? It's either you have parallel lines or you have similar triangles. If you have parallel lines, then you can play with the sides. If you have similar triangles, then you can play with the sides, right? So clearly here, we have similar triangles, so we're going to use them, right? If we had parallel lines, we're going to use the parallel lines. We know fully well our theorems. So let's look at the sides we're interested in here. We're interested in AD DE and OF, right? We have triangle ADB, and here we have triangle BDE, right? And then which sides are we looking for? We're looking for AD and DE. So because the two triangles are similar, we can say that line AD, right, on this first triangle here, divided by line DB on that triangle will be equals to line BD, right, on this triangle here, divided by line DE, right? The sides will be in proportion because the two triangles are similar, right? And then we must state here that we're saying that because we know fully well that triangle ADB is similar to triangle BDE, right? So now we can cross multiply, and then we can get DB squared is equals to AD multiplied by DE, because look here, DB is just BD, right? So we can just say DB squared is equals to AD multiplied by DE. And then we're not done, right? Here we have DB squared, but in what we are required to prove, we have OF squared, right? So let's try and find how DB squared and OF squared are related. It's not really easy to see here, but then 2OF is equals to DB. Let me tell you why, right? Don't forget that we have already deduced that F1 is 90, right? But then also D1 is 90. Because it's been subtended by the diameter, right? So if F1 is 90 and D1 is 90, then we know that OF should be parallel to DB, right? OF is parallel to DB. But because F is the midpoint of AD, then we have AF being equals to FD. If AF is equals to FD, then OF should be half of DB. So that is why here I'm saying that 2OF is equals to DB, right? So if we substitute that back in our equation, we're gonna get 2OF squared being equals to AD multiplied by DE. So it should be easy to see now that we're gonna get 4OF squared is equals to AD multiplied by DE. So now we divide in both sides by 4, right? If we do that, we get OF squared is equals to AD multiplied by DE, and then everything divided by 4. Diameter ED. So up to this point, we know we have some diameter ED. The circle is produced to C, and AC is a tangent to the circle at B. So now we know we have a tangent, and then M is a point on DE such that AM and DE are perpendicular to each other. AM and chord BE intersect at F. So now we know we have a chord. Why am I circling those words? Because they mean so much to us when you're doing Euclidean geometry. So we have 10.1, and then 10.1.1 says prove given reasons that FBDM is a cyclic quadrilateral. So we have FBDM being a quadrilateral, right? And we're supposed to prove that. So let's go to our first keyword, which is diameter, right? Our diameter is DE, and then how can we deduce that FBDM is a cyclic quad using the diameter? The diameter, the only thing it's telling us up to so far is that this angle B2 is 90 degrees, because an angle that is subtended by a diameter on the circumference is 90, right? But then if you pay close attention, you will realize that M2 is also 90, right? And then an exterior angle of a cyclic quad is equals to interior opposite, right? So we can see that B2 is equals to 90 degrees because it has been subtended by a chord. And then from there we can see that M2 equals to B2. So why are we saying M2 is equals to B2? Because they are all equals to 90 degrees, right? So from there we can conclude that FBDM is a cyclic quad. Why are we saying it's a cyclic quad? Because an exterior angle is being equals to opposite interior. And what did we use to prove that? We used the keywords we have settled, and in solving Euclidean geometry we're gonna stick to nothing else but the given keywords to answer all the questions. So now let's move to 10.1.2 that says prove given reasons that B3 is equals to F1. So where is B3? Okay, yes, B3 here. Let me just remove those 90s so that we can have more clarity on our diagram. So B3 is situated here, and then this is where F2 is, right? And then F1, I meant F1, and we are told that B3 is supposed to be equals to F1. So let's go back to our keywords, because that's all we do. We stick to nothing else but the keywords. It says the first keyword is diameter, like we have circled, and then the diameter only tells us that B2 is 90, so it cannot do much for us. So let's move forward and use the next keyword, which is tangent. So we are told that the tangent is AC, right? So if AC is a tangent, then B3 is equals to D2, right? B3 is equals to D2. So up to so far, we can just state that B3 is equals to D2 because of the Tan-chord theorem, right? But then something to realize, we have to realize that F1 is an exterior angle of a cyclic quad, so it is also equals to D2, right? So we can say that F1 is equals to D2. That is because F1 is an exterior angle of a cyclic quad, right? So let me just write that down, of a cyclic quad, and then it is equals to D2 because D2 is a interior opposite. So now we can conclude and say that F1 equals to B3 because they are all equals to D2, right? And then we are done with proving 10.1.2, and then now we can move ahead to 10.1.3. So 10.13, we have triangle CDB, and they're saying let's prove that it is similar to triangle CBE. And again, we're not going to use anything apart from what we're given. We're going to stick to the keywords to answer all the problem. So now up to so far, the keywords we have is diameter, tangent, chord. And another thing we just know that FBDM is a cyclic quad. So we can just add cyclic quad here, cyclic quad, just in case we might forget. But then apart from that, these are the only properties we are using, right? So as I've said on the other video I did on Euclidean geometry, when they name these angles, they don't just name them randomly. They name them relative to the angles that are equal. So in triangle CDB, angle C will be equals to angle C in triangle CBE. The same is true for D, and then the same is true for B. So let's draw the triangles so that we can have a bit of more clarity, right? Now we have more clarity on our triangles. So let's go ahead and start. So before you go any further, you will realize that angle C is equals to angle C on all triangles, right? So the reason would be common. They have a common angle. So now we can look for this angle D1 here to be equals to this entire angle. If we look at the diameter, it doesn't tell us much about B2 being related to D1. So we're gonna move ahead and look at the tangent. So because AC is a tangent, we've already said that B3 will be equals to D2, right? But then another thing that is true is that B1 in our smaller tangent will be in our smaller triangle will be equals to E in our big triangle, right? So from here we can say that B1 is equals to angle E because of the Tan-chord theorem. And then from here we can then conclude that triangle CDB is equals to triangle CBE. That is because if two angles in two triangles are equal, then the third angle will also be equal, because the sum of angles in triangle is constant, or it is equals to 180 degrees. So we have proved that similarity. So we have 10.2. 10.2 says if it is further given that CD is equals to 2, so CD is equals to 2. Let me just write that down. CD is 2, and then DE is 6 units. So DE is 6 units. Calculate the length of, and then 10.2.1 DE is equals to 6, and then 10.2.1 says calculate the length of BC. So what is BC? BC is this line here, which is the biggest line on the smaller triangle, right? So in using similarity, we can say that BC divided by something will be equals to the biggest side on the biggest triangle, right? The biggest side is CE, which is CD plus DE. So we're gonna have 2 plus 6 divided by. Now we have to make sure that the other sides which we're dividing with, we know their values so that we can determine BC. So we are given CD and DE. What is CD on our small triangle? CD is our smallest side, right? So we're gonna put CD there, and then the smallest side on our bigger triangle is BC. So here we're also gonna have BC. But we know what CD is. CD is said to be 2, right? So here in place of CD we can have 2 instead. So if we cross multiply, we're gonna get BC squared equals to 2 multiplied by 8, which is equals to 16, right? So what the square root of 16? We know fully well that the square root of 16 is equals to 4. So the length of BC will then consequently be equals to 4. And then we can move ahead and do 10.2.2, which says let's determine the length of DB, right? So let me just erase that marking I had done for BC, and let us look at DB. DB is our why am I erasing it? So DB is our second largest side on our small triangle, right? So we can say DB divided by and then some side is equals to what's the second smallest side in our big triangle? That is BE, right? So let's put BE there, and then divided by and then we can divide by any two sides that we have, and the length is off, and we'll still keep our proportionality, right? So for our small triangle, we know CD, right? So let's just divide by CD. CD is our smallest side, so we can say CD, and then the smallest side in our triangle, in our big triangle, is CB, right? So here we can have CB. So for DB, we still just have DB because we don't know what that is, right? And then for BE, what is BE? It seems like we also don't know what BE is, so let's just leave it like that for the moment. And then we know that CD is equals to 2, and we know that CB is equals to 4, right? So we're gonna have DB multiplied by 4 equals to 2 multiplied by BE. So basically BE is equals to 2 multiplied by DB. But the trick of the question is realizing that as soon as you have this, if you use any kind of proportionality, then you won't be able to solve for either DB and BE, right? Because let's say you're dividing 12x by 6x. This is not 2x, right? It is 2. So if you have one length in the form of another, right, and then you cannot divide your way into finding the length, because the length itself will be cancelled out and you'll only be left with the proportion. So we want to find a method which we can either add and subtract, because if you have 12x and you minus by 6x, you're going to have 6x, right? So you will still have that length there. So we want to find a way which we can add or subtract to find the length of BE and DB consequently. So there's something to realize here. We said that B2 is 90, right? So if B2 is 90, that means that triangle BDE is a right angle triangle, right? So we can say DB squared plus BE squared is equals to DE squared. But what is DB squared? So because right now we don't know what DB squared is, we're just gonna have DB squared, rightfully so, and in place of BE we're gonna put 2DB, because that's what the proportionality told us, right? So if you realize, now we're gonna be solving for DB. So what is DE? DE is 6, so we're gonna have 6 squared. So this will become what am I writing? DB squared plus 4 DB squared equals to 36. So we're gonna have 5 DB squared equals to 36. Now we can divide both sides by 5, right? We're gonna get DB squared equals to 36 divided by 5. If you take square roots on both sides, you're gonna get DB is equals to square root of 36 is 6, right? But then the square root of 5 is square root 5.
When we did question 8 and 9, we realized that you can answer all the questions using only the keywords in the statement. So we're going to try and apply the same idea to this question. So it says that in the diagram below, BCD are points on a circle such that BC is equals to CD, EC and ED are tangents, right? So tangent is a keyword because we have a theorem that talks about tangent, the Tan-chord theorem, right? So I'm going to write that down. I have tangent, and then it goes on to say that BC produce meet tangent DE produced at F, angle B is equals to X. So it seems like the only keyword we have is tangent, right? And this question is out of 17 marks. So we should get all of these 17 marks based on the keyword tangent and nothing else, right? So we're just combining the keyword tangent and just a few basics, the sum of angles on a triangle, angles on a straight line, and so on. But then in the grand scheme of things, we're answering all the questions using the word tangent. So the first one, 10.1, says, so we have 10.1 says, prove given reasons that E1 is equals to 180 minus 2x. So 10.1.1, we are asked to prove that E1 is equals to 180 minus 2x. So let's look at E1 on our graph. So here's E1 here, right? And then E1 is on triangle ECD, right? On triangle ECD, we have angle C2 and angle D1. There's nothing else we can do. We have to look at the tangent and consequently the Tan-chord theorem, right? Because that's the only keyword we have. If you look at C2, you will realize that it is equals to angle B, right? Because of the Tan-chord theorem. Angle C2 is between tangent CE and chord CD. And then chord CD subtends angle X, right? So C2 is equals to X. Why are we saying so? The Tan-chord theorem, right? We don't have much of a choice. We only have tangent. So all the questions we have to answer them based on the Tan-chord theorem. And then at the same time, D1 is also equals to B, right? Because D1 is between tangent DE and chord CD. And as we have said, chord CD subtends angle B, right? Which is X. So now we can say that D1 is also equals to X. So now you will realize that E1 plus C2 plus D1 should be equals to 180 degrees, the sum of angles on a triangle. So now we can find E1 by saying that it will be equals to 180 minus C2 minus D1, which are all equals to X. So it's 180 minus 2X. And then that's how you find E1. Now we can move to 10.1.2. 10.1.2, we still have one keyword, right? Proving that angle E1 is equals to 180 minus 2x doesn't give us any other keyword. So we're supposed to answer 10.1.2 using the tangent again, because that's the only keyword we have. So we're supposed to prove that triangle ECD is similar to triangle CBD. So let's look at these triangles on our sketch. So we want ECD. So here's ECD here. And then we're supposed to prove that it is similar to triangle CBD. So we have C going to B and back at D. So when you're proving similarity, you need two angles to be equal to each other. As soon as two angles are equal to each other, the other two remaining angles will be equal to each other, and you will have proved that the two triangles are similar, right? So the way the examiners name their triangles, right? They name them with respect to the angles that are equal. So angle E in triangle ECD should be equals to angle C in triangle CBD. And then angle C on triangle ECD should be equals to angle B, because it's the second letter of how they name the triangle, right? And then angle D on ECD should be equals to angle D on CBD, right? So let's start with angle E on triangle ECD. So angle E on triangle ECD is here, right? It's E1. We know that it's 180 minus X. So we're saying that angle CE should be equals to angle C on triangle CBD. So it should be equals to this angle. And indeed they're equal, because I want you to realize something. In triangle CBD, right, C3 will be equals to 180 minus 2x. Why am I saying 180 minus 2x? Because B, we've already established that it is x, right? But this angle D2 here will also be x, because line CB is equals to line CD, right? So C3 will be 180 minus x minus x. So we have proved that C3 is equals to E1. Now we can move to the following angles. So we're saying that angle C in triangle ECD should be equals to angle B in triangle CBD, right? So angle C in triangle ECD, it's C2, right? And then we have already proved that it's equals to angle B because of the Tan-chord theorem. So now we can see that C2 is equals to angle B is equals to x. Why are we saying so? Tan-chord theorem, right? Now we've proved that two angles are equal in these two triangles. So the third angle, without proving it, already we know that it is equal, because those angles should all add up to 180, right? So now we are basically done. We can conclude that indeed ECD is similar to triangle CBD. Pay attention to the letters next time you solve this kind of problems. It always works. And then let's move to 10.2. 10.2 is saying to us, we have 10.1, which says prove given reasons. So we have 10.2.1 is saying that CD squared is equals to CE multiplied by BD, right? Let me just clear these sketches up so that we can have a bit of more clarity. So we want CD squared. So we want CD squared to be equals to CE multiplied by what? Multiplied by BD. Multiplied by BD. So if you pay attention here, these sides that we're interested in are sides on our similar triangles, right? So we can use the fact that those triangles are similar to find 10.2.1. So we moved from the word tangent, and now we have figured out that we have two triangles that are similar, right? So we can use similarities as one of our keyword, right? But then we're not just taking it out of thin air. We're using it because we have proved that indeed they are similar. So for 10.2.1, we're going to use similarity, which we proved through the Tan-chord theorem, our main keyword. From what we are required to prove, you can see that we some way somehow need CD, right? And then apart from CD, we need CE and BD, right? So our proportionality should involve those sides, right? From what we are required to prove. So let's start with CD. So we can say that CD divided by something. So CD is the smallest side of triangle CBD, right? So let's say CD divided by BD, right? The biggest side of triangle CBD. And then let's do the same thing on triangle CED. So the smallest side on triangle CED is CE, right? So we're gonna say CE divided by the biggest side on that triangle, which is again CD, right? And then that should be true if the triangles are similar. So now from here, we can cross multiply. So we can say that CD multiplied by CD will be equals to CE multiplied by BD, right? And you will see that CD squared will be equals to CE multiplied by BD. If you take a ratio of the smallest side to the biggest side on one triangle, it will be equals to the ratio of the smallest and biggest on the other triangle, right? It doesn't have to be smallest and biggest in that order. You can do it in any other way. But then as long as you do the same thing on the two triangles, the ratio of the two sides must be equal to each other. And that's how you would do 10.2.1. So the way you justify what I just wrote here is by stating that triangle ECD is similar to triangle CBD, right? And then let's move to 10.2.2. 10.2.2, we are required to prove that CF squared divided by EF squared is equals to BD divided by DE, right? Which is a bit complicated, but it's fine. So CF is not in any of those triangles, so we cannot use those triangles to prove 10.2.2. we have to resort to something else, right? But take a look at this. If line CE is parallel to line BD, then it will be quite easy to say that CF divided by EF will be equals to something, right? But then, are they parallel? Let's look at that. We know fully well that if they're parallel, then we can construct something like this. Not really construct because it's already there, but then this angle C2 should be equals to this angle D2. That's if the two sides are parallel. And then guess what? That's true because C2 is equals to X, and then D2 is also equals to X. So C2 is consequently equals to D2. So by saying that, we've basically proved that CE is parallel to BD, right? Because we have those alternate angles being equals to each other, right? And then now, since we've proved that, we can see that BC divided by CF is equals to DE divided by EF, right? We can play around with things like this once we have proved that CE is parallel to BD, right? We can play around with those ideas, but that's not where we're going. That's not what the question is asking us. We have to look at CF and EF, right? We are guided by the question. So let's say CF divided by EF and see where that can take us. So if we say CF, right? CF is this line divided by EF, then we can say CB divided by DE. The two lines CE and BD are parallel, so we can get away with that. So let's see that. So saying that CF divided by EF will be equals to BC divided by ED. And why are we saying that? CE is parallel to BD. We can get away with that. So now we have CF squared and EF squared. We know fully well from grade 3 that if A is equals to B, then A squared should be equals to B squared, right? No questions asked. The other way around is not necessarily true, but then if A is equals to B, then A squared should be equals to B squared. So we can say CF squared divided by EF squared is equals to BC squared divided by ED squared, right? And then that's it. We're still not quite there. What else are we missing? Okay, 10.2.1. Now we know from our sketch that BC is equals to CD, right? So if BC is equals to CD, then BC squared should be equals to CD squared. And we know exactly what CD squared is equals to from 10.2.1, right? So in place of CD squared, we're going to put CE multiplied by BD. Here it is. So now we can say that CF squared is equals to EF squared. And then in place of BC squared, we put in CE multiplied by ED. So here we can have CE multiplied by BD, right? Divided by DE. But we're not divided by B or DE squared, right? But we're not quite there yet. We need DE on the numerator, right? So that we can lose that square on the denominator. So which one between CE and BD is equals to DE? Let's look at our sketch. So let me remove a few things for clarity. So we know that this angle here is X, this angle here is X, and then here we have X, and here we have X. So if we have X here and we have X here, then CE should be equals to DE, right? So in place of CE, we're gonna put DE. So we have CF squared being equals to EF squared, which is equals to, in place of CE, we put in DE multiplied by BD divided by DE squared. So DE and DE, we are left with CF squared divided by EF squared being equals to BD divided by DE.
The answers to this question are actually on the question itself. Let me show you what I'm talking about. So this question here is saying that in the diagram below, A, B, C, D, and E are points on a circle centered at O. AC, OC, and ED are drawn, and then chord BC is equal to chord CD. So let's just go ahead and write that down. So we're saying that chord BC is equal to chord CD, right? And then we are told that let's let angle CED here be equals to X, right? And then let's look at our diagram. If you look at our diagram, you will realize that AOD is a diameter, right? There it is. So here in our keywords, let's just write diameter. Why are we writing that down? Because it's important in Euclidean geometry, right? So essentially, we should be able to solve our problems with only these two keywords here and nothing else, right? Except from just the basics, sum of angles in a straight line and so on. So let's look at 8.1. So we have 8.2.1. So 8.2.1 says that determine with reasons two other angles which are equals to X. So we are told by the first keyword, right, that chord BC is equals to chord CD, and we know fully well that equal chords subtend equal angles, right? So if you can see here, you will realize that chord CD subtends X, right? And then chord CD is equals to chord BC, and chord BC subtends A1, right? Equal chords subtend equal angles. So what are we saying now? We're saying that angle X is equals to A1, and then the reason for that is that equal chords subtend equal angles, right? Now let's look at our second keyword, diameter, right? What do we know about a diameter? All we know is that it subtends an angle on the circumference of a circle of 90 degrees, right? So this here is 90 degrees, but then that's all we know, nothing else. So let's go back to our first keyword and see how we can use the cos to find another angle which is equals to X. So you will now realize, if you haven't already, that not only does chord CD subtend this angle X here, but then it also subtends this angle A2 here. So that angle A2 is also equals to X because they have been subtended by the same chord. So now we can say that X is equals to A2. Why are we saying X is equals to A2? They have been subtended by the same chord, right? They've been subtended by the same chord on the circumference of our circle. So we have done 8.2.1. We can now do 8.2.2. So 8.2.2 is saying that let's determine the size of angle ABC in terms of X, right? So let me just clear these lines that I've drawn here so that we can have a bit of clarity. So we want the size of angle ABC. Yes, angle ABC here. Just place the dot. So again, we should be able to find the size of angle ABC just sticking to the basics and the keywords we have, right? In triangle, so let's regard triangle ACD, right? So in triangle ACD, you will realize that here A2 is X, right? So if you say that A2 plus this angle, which is 90 degrees, right? plus angle ACD plus D1. This should be equals to 180 degrees, right? The sum of angles in a triangle. So now we're gonna have A2 is X, and then angle ACD, that is 90 degrees, right? And then plus D1 should be equals to 180 degrees. So D1, if we solve for D1, we shall get 180 minus 90 minus X. So D1 should be 90 degrees minus X, right? So this angle here, D1, we're saying that it is 90 minus X. Now what you have to realize is that A, B, C, D is a cyclic quad, right? All the corners of this quadrilateral, they are lying on the circumference of the circle. So what does that tell us? We know fully well that the opposite angles of a cyclic quad add up to 180, right? So we say that D1 plus our angle ABC that we're looking for, plus our angle ABC should be equals to 180 degrees, right? It's the basics, it's not me. So what is D1? We know fully well that D1 is 90 minus X, and then plus ABC should be equals to 180 degrees. If you solve for ABC, you're gonna get ABC being equals to some 180 degrees minus 90 plus X, right? So 90, when you take it to the other side, it will become minus 90, and then minus X, it will become plus X, right? So ABC will be equals to 180 minus 90, that is 90 plus X, right? And we have determined the size of angle ABC. And then last but not least, 8.2.3 says, let's prove beyond reasonable doubt that AB is parallel to CO. So let's, go ahead and look at AB and CO and see what we can do there. So we have AB here, and then this is CO. And they're telling us that these two, they're parallel, right? And we're supposed to prove that. If they're parallel, then this angle here, A1 plus A2, should be equals to angle O1, right? Corresponding angles, right? So we're saying that we need A1 plus A2 to be equals to O1. This is what we are required to prove, essentially, right? So let's see what we can do here. We know that A1 is X and A2 is X, right? So A1 plus A2 should be equals to X plus X. So this is equals to 2X. So if we find a way to say that O1 is equals to 2X, then we are done with our problem, right? But then I kid you not, if you look here, you will realize that O1 is an angle at the center, and it should be 2 times the angle at the circumference, right? So O1 here should be 2 times angle E, right? And angle E is X. So now it will be easy to see that O1 is equals to 2 multiplied by angle E, right? Why are we saying that? The angle at the center should be 2 times the angle at the circumference, right? So you write that down. We're saying that the angle at the center should be 2 times the angle at the circumference, right? So now we have O1 being equals to 2 multiplied by X. So now A1 plus A2 is indeed equals to O1 because they're all equals to 2X. And then by saying that, we've essentially proved that our line AB is parallel to CO.
When it comes to cycle geometry, getting the keywords right from the statement is the most important thing, because with the keywords, you are then able to answer all the questions. If you're wondering why I'm starting with 8.2, 8.1 was saying let's prove the Tan-chord theorem, and we've already done that. I will leave the link in the description. In the diagram below, PWRS is a cyclic quadrilateral. So cyclic quadrilateral, I'm writing that down. So we have cyclic quad, and then the circle is centered at O. PSW is an equilateral triangle. So I have triangle PSW, which is equilateral, equilateral. So when a triangle is equilateral, all the angles are equal. The only way all the angles can be equal is if all the angles are equals to 60 degrees. TW is a tangent to the circle, so we have tangent. And then we have radii OR, right? Radius OR, so let's say radii. And then OW are drawn, and then we are told that W1 is equals to 25 degrees. So all the questions that we are going to answer, we are going to stick to these keywords, except from basic things like angles on a straight line and so on. So 8.2.1 A says determine given reasons the size of S1. So we are interested on S1. Yes, S1 here. So how can we use cyclic quad to determine S1? S1 is not a complete angle, right? So I don't see how we can immediately jump to S1. The next keyword talks about triangle PSW being equilateral. S1 is not in that triangle, so I don't see how we can use that. And then the third point talks about the tangent. We have tangent TW, right? And this is how we are going to determine S1. Look at W5. W5 is between TW and RW. And then at the same time, RW subtends S1. So S1 will be equals to W5. It will be equals to 25 degrees. And why are we saying so? Tan-chord theorem. And then let's move to B. B says let's find O1. Again, we're not thinking about anything else other than the four keywords we have. Cyclic quad, there's no immediate connection between O1 and the cyclic quad. Angle PSW, O1 is not an angle on PSW, right? So it cannot help us with anything. And then tangent, O1 is at the center of a circle. There's no immediate way that is connected to a tangent, right? Because usually when we're talking about tangent, we're talking about the Tan-chord theorem. And now the only option we're left with is radii, right? Let's look at how radii can help us. Obviously, OR and OW are equal to each other. So angle R2 will be equals to angle W3 plus W4, right? We're saying that this angle here is equals to this angle here. So now we can say that O1 is equals to 180 minus 2R2, right? Because we're gonna minus R2 and we're gonna minus W3 plus W4. But we know that W3 and W4 is equals to R2. So minus 2R2. So if we can find a way to find R2 or W3 and W4, then we can find angle O1, right? OW is a radius, right? And it touches the tangent. Where it touches the tangent forms an angle of 90, right? We know that for sure. So now we can say that W3 plus W4 plus W5 is equals to 90 degrees. I'm talking about this angle here, right? But we know what W4 is. We know what W5 is. W5 is 25 degrees, right? So we're going to have W3 plus W4 being equals to 90 degrees minus 25 degrees. And that will be equals to 65 degrees. So now in place of R2, we can put 65 degrees. So we're going to have O1 being equals to 180 minus 2 multiplied by 65, which will be 130. So O1 is equals to 50 degrees. We just stick into the keywords and nothing else. So A has 2 marks, B has 2 marks, and then C has 5 marks. And then now let's do 8.2.2. 8.2.2 says let's prove that SP is parallel to TW. So we're proving that SP is parallel to TW. Obviously, we don't have coordinates here. So there's no way we're going to be calculating the gradient. We have to do that using angles some way, somehow. So if these two lines are parallel, then this angle here, W1, should be equals to this angle P here. But then at the same time, W1 should be equals to S2. Why are we saying that? To our keyword again, tangent. We're using the Tan-chord theorem, right? We're sticking to the keyword. So now we can say that W1 is equals to S2. We already said that S2 will be equals to 60 degrees, right? Why are we saying S2 is equals to 60 degrees? Because triangle PSW is an equilateral. So W1 is equals to S2, but S2 is equals to SPW. They are angles on an equilateral triangle, and all those angles will be equals to 60 degrees. And we're done with 8.2.2. We can give a reason and say that they are alternate angles. And then let's move to 8.3. 8.3 says, in the diagram below, a circle centered at O is drawn. H, J, G, and L are points on the circle. Triangle HGL is drawn. HOG bisects GL and M. So we have 90, and then we're given the values of the lengths. And then 8.3.1, if MG is equals to 6 units, so let's denote MG, right? So we are told here that MG is 6 units and OM is X units. So we have X here for OM. Write HM in terms of X. So let's look at HM. So H starts here and then it goes down to M, right? So we want the length of HM in terms of X. HM is basically equals to 2 radius minus mg, right? Because if we're looking for hg instead, then it will just be 2 radius, right? But then the only difference between hm and hg is that hm stops here at m, and then we have that 6 going forward. So hm is basically 2 radius minus mg. But what is the radius? We have OH as the radius, right? But then OG is also a radius. So let's write the radius in terms of OG. So if we write the radius in terms of OG, it will be X plus 6, right? From here at O to M and from M to G, it will be X plus 6. So if we substitute that in place of the radius, we're gonna get 2x plus 6 and then minus mg, which is 6, right? So that will be equals to 2x plus 2 multiplied by 6, 12 minus 6. So hm will be equals to 2x plus 6 units, right? And then now we can move to 8.3.2. Calculate, given reasons, the length of the radius of the circle. So we already know that the radius of the circle is equals to x plus 6, right? So on this question, we can use triangle OJM, right? Let me just clear something so that we can make it more clear. We are looking at triangle OJM, right? We have the radius of triangle OJM, which is equals to the radius of the circle. So that will be x plus 6, and then we have 12 as the adjacent, and then x as the opposite, right? So we know fully well that on a right angle triangle, don't forget the angle here is 90, the radius squared will be equals to x squared plus y squared, right? The other two sides. So what is the radius here? The radius is x plus 6. So we square it and it will be equals to the adjacent, which is 12. So we're going to have 12 squared plus the opposite, which is x. So we're going to have x squared. So what is x plus 6 squared? X multiplied by x is x squared. X multiplied by 6 is 6x. You multiply that by 2, you get plus 12x. And then 6 multiplied by 6, that is 36. And that will be equals to 12 squared, 144, plus x squared, right? So look at this. We have x squared here, we have x squared here. So they're going to fall off, right? We're going to be left with 12x plus 36 is equals to 144. So 12x is equals to 144 minus 36. So we have 12x being equals to 108. You divide both sides by 12, you get x is equals to 9, right? But then we're not looking for x, we're looking for r, right? And we know fully well that r is equals to x plus 6. So that will be 9 plus 6, 15.